Okay, so today what I will do is I'll essentially present an algorithm, a framework to solve quadratic optimization problems under combinatorial constraints. Sparse PCA, as we'll see, is actually a problem that can be written in this form. And actually, it covers other extensions beyond sparsity, although we use sparsity today as an example application. Okay, so first, a brief overview of PCA. PCA, principal component analysis, is a classical dimensionality reduction tool. It's used as a preprocessing step for many machine learning tasks like classification or prediction when we are trying to build a simpler model. Sparse PCA, or PCA with other constraints like nonnegativity or other possible structure on the extracted components, are variants of the original problem where we are actually imposing combinatorial constraints to the components we are trying to find, so the basis on which we will project the data. And these kinds of constraints make the problem NP-hard, but we are still interested in imposing them because we get some results that are more interpretable. So we get components that can help us get insight into a physical system, or they can help us build a model, for example, that may be more robust to generalization. Okay, so what I will do today is basically present a novel framework for dealing with problems like sparse principal component analysis, and this framework comes with some form of spectral guarantees. So I know that Sparse PCA is not the go-to tool for text analysis, but I'm going to use this document analysis example as a motivating application, mostly because I find it cute and it's easy to for exposition purposes. So let's say that you have a bunch of documents, a single document, or you can think of it as a tweet. So a small collection of words, and let's say that we represent this document with a bag of words model. So every document corresponds to a binary vector. The dimensions in the vector corresponds to words of the English dictionary, and a word has value 1. I mean, the ith entry in the vector has value 1 if the corresponding word appears in the document or tweet. Okay, very simple. And let's say that we have a bunch of documents now. So this is our data set. We have m documents all in n dimensions corresponding to the words. So this is our m by n input data matrix. Using this data matrix, what we can do is we can compute a correlation matrix, a word-by-word co-occurrence matrix. So S is my data matrix. SS transpose gives me this n by n PSD matrix A. And the ijth entry tells me how many times word I appears together with word j in my class of documents. Okay? So PCA is the problem of this optimization problem. We are trying to maximize the quadratic form x transpose AX over all unit norms vector x in this matrix A, the correlation matrix, which is given as an input. Now, most of you will be familiar with this. The solution x is the principal eigenvector of A. This problem, although it's non-convex, we can actually easily solve it by computing the singular value decomposition of A. And what the objective function does is essentially it captures the explained variance, the amount of variance we can capture if we use x and project data on the direction of x. So we refer to this objective as the explained variance. And the principal component, what it does is it finds this direction where if we project the data, we actually maintain most of the variability of our data. Okay, so this is the vanilla version of PCA. It's a useful dimensionality reduction tool. But, and let me just say, besides this optimization, like the formulation as an optimization problem, what we are trying to do in the context of this text analysis problem is we are trying to find a vector x, which will now correspond again to an n-dimensional vector in the space of words, that basically aligns as much as possible with the documents that we have in our class of documents. So we are trying to find a document that somehow represents as much as possible the documents in our corpus. Okay, the problem with vanilla PCA is that the vector that we will find will always be dense. So we have n words corresponding to the n dimensions corresponding to the n words in the English dictionary, or at least the words that appear in our corpus. So we will find a vector x that corresponds to a pseudo document, a representative document, but all words that appear in my corpus will get some weight. So if I look at this document and I'm trying to get an idea of what my corpus looks like, what kind of documents are there, then I don't really have any hope of getting a good idea. And that's where constraints like sparsity come into picture. Maybe I'm interested in enforcing sparsity and saying, OK, I want to still find a document that will align with most of the documents in my dataset, so a document that represents my corpus. But I want this document to only consist of a very limited number of words, because limited number of words is an interpretable document. And this is actually, we did this. We ran Sparse PCA with our algorithm on a text dataset. This is from the New York Times dataset. And we get vectors that look like this, like cup, minutes, tablespoon, oil, teaspoon. So looking at a document like this, you get a very good idea of a topic like recipes is actually, it appears in your corpus. OK, so a little bit more abstractly now. So again, in the vanilla PCA case, what we have is input data points. So we have some samples in arbitrary dimensions. Here I'm drawing them in 2 dimensions. My variables are v1 and v2. These correspond to words in the previous example. The objective is to find the direction, like the red arrow, that capture most of the variability in my data set. So I'm trying to find the direction such that if I project all my data points across this direction, I still capture most of the variance. And in this case, the direction is a linear combination of both variables, v1 and v2, with some non-zero coefficient. Okay, and we said as an optimization problem, to find this direction, it's actually the solution, the desired direction is the solution of the quadratic maximization x transpose AX on the empirical covariance matrix A that is computed given the observations, the 2-dimensional observations in this case. Okay, and again, this problem is non-convex already just by the fact that we are trying to maximize a quadratic form on a positive semidefinite matrix. But fortunately, it's very easy to solve through singular value decomposition. Now, we want to impose sparsity on it. We want to find a direction that captures most of the variance, but at the same time it's sparse. What does sparse mean? It means that we want to find a direction that is a linear combination of the original variables, but not all of them. We want actually the coefficients for most of the original variables to be 0. In this case, I only have 2 variables, v1 and v2, so the only thing I can do to claim a sparse solution is say that the desired direction aligns with one of my 2 variables. But you can imagine in higher dimensions, I'm just looking for a vector where most coefficients are 0. And how do I get this sparse solution? Well, I go to my optimization problem, and I straightforwardly incorporate this L0 norm constraint. The L0 norm counts the number of non-zero entries in the vector. So I'm explicitly saying, you will give me a parameter s that's smaller than my dimension n. This is the limit on the number of non-zero entries. And I'm just incorporating a constraint in my optimization problem. And that immediately makes the problem NP-hard. And the hardness comes from the fact that I need to determine the support of this vector x. So again, I'm trying to find a vector with at most s non-zero entries. I don't know which ones will be non-zero. If I knew, then the problem is easy. Why? Because I can, so for example, if someone tells me these gray entries, if you can see gray, will be the non-zero ones, then you can restrict your attention in the corresponding submatrix of A, compute the principal eigenvector there, and then everything else is 0 anyways. So the hardness comes from determining what the support of my solution is. Okay? And let me just say, besides sparsity, we could have other constraints. We could have constraints like non-negativity. the same observations apply. Even if I ignore the constraint on sparsity and I only ask for a non-negative vector, my problem is still NP-hard for the same reasons. In fact, the hardness comes from the need to determine the support. Someone might say, why am I interested in a non-negative vector anyways? Well, again, interpretability is what comes into the picture. Let's say, for example, in my document analysis example, I'm interested in pairs of words that tend to appear together. So I'm interested in positive correlations instead of just arbitrary correlations. Okay, so in the remaining, I will just focus on sparsity for simplicity, but just keep in mind that most of the things I will say basically extend to other cases.
Is it for your sparse thing, if S is very small, like log n or something, is it still difficult?
I mean, no. So we will get to that, because the naive solution would be to exhaustively consider all supports. Yeah, I mean, so if it's too small, if it's constant, for example, you can say that in polynomial time I can consider all possible supports. Now, if it's logarithmic, I don't know, maybe there is something intermediate and more targeted you can do. But here we are thinking actually the case where S is arbitrary. So we will allow S to be a fraction of your dimensions. So someone can say, I want to find a component that is 10% of the entries are non-zero. Okay? Good. Okay, so the problem has been around for a while. It's been looked by several communities. In statistics, people are interested in the problem from a completely different perspective. I'm looking at this more as an optimization problem, and I'm interested in the interpretability aspect of the output. But there has been several algorithms dating 20 years back. We have simple techniques like rotation. We try to find some basis and then rotate it to find a sparse basis within the principal basis. There are convex formulations with various forms of regularization. Greedy techniques where they try to find the support and expand it greedily one element at a time. Power method, a truncated version of power method similar to computing the principal component. Frameworks based on expectation maximization, assuming some underlying probabilistic model. And the thing is, most of these techniques don't come with guarantees. They are basically heuristics. There are some recent exceptions, again, under assumptions. So from the point of view of statistics, we say, OK, if we have some model, some true sparse component, and then we have a population of data generated based on this component, there are some approaches that mostly based on semidefinite programming that can actually, they promise to recover the true principal direction. Okay? Now, what I will do today is actually I will present an algorithm for Sparse PCA. My algorithm is combinatorial in nature. And what it gives is a hierarchy of approximations. So there's going to be a trade-off between the computational complexity and the quality of the guarantees. OK, so here is our main result. This is the optimization problem I'm interested in. Okay, A is an n by n positive semi-definite matrix. This is given to me. I'm trying to find a vector x that maximizes the quadratic form. It's unit norm and has at most s non-zero entries. S is a given parameter. We have a new algorithm to attack this problem. Our algorithm comes with spectral guarantees. It has the following form. So you give me the input matrix A. You give me an accuracy parameter R. And n is the dimension of my input data. The algorithm will run in complexity n to the r. And it will output a vector x sharp with at most s non-zero entries. And what I guarantee you is essentially that the objective value that I will attain is at most this far away from the unknown optimal value. Okay, so x star is the optimal S sparse vector that I'm looking for, and lambda in subscript r plus 1 denotes the r plus 1th eigenvalue of my input matrix A. You had a question.
What is R exactly? The accuracy parameter is the number of the eigenvectors?
I'll come to that. Great. So R for now is an accuracy parameter. Maybe you suspect it has to do with the low rank approximation of A I'm going to use. So basically, that's what it corresponds to. My algorithm, instead of operating on the original input A, it will operate on a low rank approximation of A. R denotes the rank of the approximation. So the higher the R is, the more complex the computational complexity is required to get the solution, but better results because this tail vanishes. I mean the error. Okay. So the key machinery that I'll be presenting is essentially how do I solve the same problem when my input matrix is actually low rank. That's what I'll be mostly interested in. Okay. Before we get there, just a minor remark. So building on this theorem, we can actually get some results as corollaries. So for example, if we have some assumption on the data like some spectral decay, actually any decay, but let's say some power law decay, then I can say things like the following. So you give me any parameter epsilon you want, as small as you want. Of course, a target sparsity S, and if this target sparsity is actually linear, grows linearly with the dimension n, then I can guarantee that the output x sharp will actually be arbitrarily close to the optimal objective. So I get a multiplicative factor approximation guarantee. So, and I get this with an algorithm that is polynomial in the parameters of my problem, the dimension n, the target sparsity S. So basically, this is what we call a polynomial time approximation scheme. Okay. So we get a pitas under assumptions. Okay. So how does it work? High-level overview of the algorithm. Input is an n by n positive semidefinite matrix, the correlation matrix of my dataset, an accuracy parameter R, and of course a target sparsity S, how sparse I want my extracted component to be. The first step is to compute a rank R approximation of the input. I will denote from now on this matrix with the subscript R, just to remind you that now we are talking about a rank R matrix. Then I solve the sparse PCA problem on the low rank matrix. Okay? The algorithm will have two steps. Essentially, I will first try to find the support for the optimal solution. And as I said, I will create a collection of supports, and I will guarantee that the optimal support is one of them. And then I will just exhaustively compare the supports, because once I fix the support, it's easy to get the optimal solution. Okay? And then the algorithm will output a vector, and then based on my parameters, and specifically the accuracy parameter that the user chooses, and also some data-dependent characteristics, like what kind of spectral decay I have, etc., I can get some guarantees about the quality of my output. Any questions? No? Great. Okay. So the remaining of this talk is how do I actually solve this low-rank problem. Okay. Once again, I'm interested in this quadratic maximization, x transpose ARX. A subscript R is now the given input. It's a rank R matrix. And I want to maximize this quadratic form over all unit norm vectors that have at most S non-zero entries. S is a given parameter. Okay, a couple of observations. I already mentioned this, but if we knew the desired support, then it would be easy to solve, because I would just focus on the corresponding submatrix of my input argument matrix. The other thing that we discussed earlier is the naive brute force way to go about solving this problem would be to try all possible supports. So I have an n-dimensional vector. At most, S of the entries will be non-zero. I could try all n choose S possible supports. Based on the previous observation, if I fix the support, it's easy to find the solution. I would compare everything and just find the optimal one. But of course, that doesn't have any hope computationally for any reasonably large S, let alone if S grows with the dimension n. So the key thing that helps us move forward with our solution is that if the input matrix is low rank, it has rank R, then we can show provably that we don't need to consider all n choose S supports to get the optimal solution. We can actually construct a much smaller set of supports and prove that within this set, the optimal support will be a member of this set.
Asteris n choose R.
That's correct. Almost. Yeah. N to the I. A little better. Well,
So
same
then
word.
you wrote down the right one, but I think it's maybe a big key level. What was that?
Yeah. I mean, I wrote it this way to compare with this.
But
But
still, this one is a big value, yeah.
It can be, but think of R as a parameter that in practice will choose like 2 or 3 or 4.
R is 2 or 3 or 4.
I mean, it's your choice, okay? But it's still interesting that we can do something like that compared to the naive. Whereas, what would you do if someone told you n is very large and then I want s to be 10% of n?
Then you usually choose R as like 10% of n.
No, R is a parameter of my choice. So n is the dimension of the entire vector. S is the limit on the, okay. And if that could possibly be like pretty big, like 10% of the dimension. Okay, so this would be huge, n choose s. R is a parameter of my choice.
You can choose R in a way that, so if you choose R like exactly as S, then it means that you have like S eigenvectors.
Sure, yes, no, yes. But there's no point in doing that because
You usually choose more than S or less than S?
way less.
Way less?
R will be way less than S.
I see.
Okay. I mean,
How you choose R depends on how your eigenvalues decay.
yes.
So
In theory, so there are two things here. There is a theoretical problem and there is a practical problem. In the theoretical problem, you choose R based on your spectral decay, the kind of guarantees that you want, and the computational complexity you can afford. So R controls this trade-off. In practice, we will see you can actually ignore all that. You can play with the higher value of R and get best results in a limited amount of time. So you can play and see what gives you the best results.
So you'll have some practical numbers on what R should be. Or you have some.
I mean, if in practice we play with R, think of it literally as 2, 3, 4. Okay? 5 is perhaps the largest one that I have tried in a dataset, but not that I ran an algorithm n to the 5. I'll show you later that you can actually run it in a smaller time and just get best results in this amount of time. You had a question?
So when you're using a vector space model for word similarity, typically R is about 300.
Okay.
So if you're telling me I need to set R to 5, I'm thinking that's way too low. You're going to lose all of the meaning of the words.
Sure. I mean, there are definitely examples. Let me put it this way. Even if you see how statisticians look at sparse PCA, I said that usually even in the simpler model, they say there is a really sparse component that it's my true component, and I'm trying to recover this. And of course, they're interested in the SNR, the signal to noise ratio, how small can it be, and then still have a hope of recovering this true component. So already by doing a low rank approximation, you might end up losing your signal. So this approach may be unsuitable for that model. Or perhaps you have a problem in a setting, to come to your question, where doing this low rank approximation step is already a bad idea. But I'm thinking cases where, first of all, we have seen in practice that in several examples that we have run it on, and since everyone is trying to solve this optimization problem, in terms of the optimization problem, we perform better with existing approaches. And another answer is there are several datasets that actually are already low rank. Because, for example, in science, you might have guys going into the fMRI machine and then collecting measurements. But the dimensions are large, although there are very few patients that go into the fMRI machine. So in that setting, your problem is by nature already low rank. Of course, it may be in practice, but
So what I hear you saying is if my interest is in the semantics of words, your technique isn't useful for me.
I cannot say that. We will have to go and play and see. But what I'm saying is that there is definitely cases where if your signal satisfies certain properties that are a little hostile towards my algorithm, I'm not saying that this is an algorithm that can address all problems on sparse PCA. Already, the fact that you rely on this low rank approximation is a weakness because there are cases that we cannot handle in theory. That's what I'm saying. Okay. Anything else? Okay. So how do we go about solving this low rank problem? The input matrix is an n by n positive semidefinite matrix of rank R. I can compute a factorization into a product VV transpose. V is a thin and tall matrix. It's n by R, R being the rank of my input matrix. So I can essentially rewrite my objective function, the quadratic objective function, as a norm, x transpose V, a Euclidean norm squared, right? And in the special case that my input is rank 1, now this is an extreme case, this matrix V is actually just a column vector, okay? So let's see how we are actually going to solve the problem if the input is just rank 1. This is the simplest case.
Yes. This scenario is equivalent to the case that R is 1.
Mm-hmm.
So we are solving for a special case of R1 and the empirical version, just to make sure that I understand. You're solving for R equals to 1.
Mm-hmm. Yeah, so now I'm assuming already that my input is low rank because I computed the low rank approximation in the first step of the algorithm. And now I'm considering the simplest case. Let's say that the parameter R is equal to 1. You would not do that, but let's see how you solve the problem. Okay, so again, I have replaced the quadratic objective with this inner product square. This is now the objective function of my optimization. So how do we solve this? I'm looking for a vector x that is unit norm and has at most s non-zero entries. You might be able to see that essentially what I want to do is align my vector with the largest, like I will choose the non-zero entries of x to correspond to the largest entries of this vector v, okay? So through an example, we are given v, this is the input to the algorithm. The target sparsity s is also an input. Let's say that we are looking for a 2 sparse vector. So the way I'm going to build x is look at the entries of v, sort them by absolute value, choose the 2 largest ones. So this case is the orange and the yellow one. This determines the support of my solution. And then to get x, all I have to do is just normalize to make sure that the length is equal to 1. Okay? And this is the optimal solution for this rank 1 sparse PCA problem. That was pretty easy. So all we had to do is actually sort the entries of this input vector v. So we solved the rank 1 sparse PCA problem in order n log n. In fact, we don't even have to sort. There is a slightly more tricky and clever way to get the s largest entries, so we can solve this problem in linear time. Questions? Yes.
I think S should also come in that complexity, right? It should be n log S. Like
For the sorting?
if you don't do the sorting on all of the elements, at least you need to, depending on the number of the S should come in that complexity.
Oh, S and like S are constant.
No. S is not constant. But the answer is no. I believe, I'm pretty confident, maybe I'm wrong now because you make me doubt, but if you're looking, for example, for the kth largest element in an array, there is an order k algorithm. So order s or order n, because s can be up to n. Once you find that, just by comparison, you can find all the entries.
Yeah, that's true. N is bigger than S.
Yes. Okay. So how do we solve the rank 2 problem? So rank 2, this is the objective function. It's a norm. So now matrix V has 2 columns. Okay, it's an n by 2 matrix. First observation, by the Cauchy-Schwarz inequality, this is my objective function, okay, the norm of the product x transpose V. So this is lower bounded by the product of x transpose V with a small 2-dimensional vector C that is unit norm. And in fact, this inequality holds for all 2-dimensional unit norm vector C, okay? Not only that, but Cauchy-Schwarz inequality says that no matter what your matrix V is, if you fix an x, there is always a vector C that can achieve this with equality, okay? Any objections to that? Okay. So the second observation is that if I fix this vector C now, okay, the inner product VC becomes a vector. So this inner product becomes a vector. So essentially, the objective function is now a rank 1 problem, which we know how to solve. Agree? And of course, what I have done is with introducing this auxiliary variable C, I'm just rewriting my problem as a double maximization now with respect to x, the sparse vector that I was looking for, and this new auxiliary variable C, which is just a unit norm vector, and it's also low dimensional. It lies in 2 dimensions. Okay? Okay, so let's go through an example to see how we will actually solve this problem. This is my objective function. I have just written the maximization on, this is a maximization on both x and c. We are given this input matrix V, it's 5 by 2, because we are looking at the rank 2 case. And let's say that again my target sparsity S is equal to 2. So how do we find x? So let me do the following. The rows of V are 2-dimensional points, so I can plot them on the 2-dimensional plane, right? The same thing happens with the vector C. So C is a variable that is 2-dimensional, so I can also draw this on the same plane. And let's say, for now, that an oracle has revealed the optimal value of C. So now we have seen already that if we fix C, I mentioned earlier that this is just a column vector. I'm trying to maximize as an inner product. And this is the rank 1 case, which we know how to do. All we need to know is the magnitude of these entries in VC. So these entries are nothing but the length of the projections of these points on this direction C. Okay? So I project these points along this direction. Again, C is a given direction for now. I compute the lengths. These are the lengths. And then just by observing at the lengths, I can say, oh, the yellow and the orange point are the ones that correspond to the largest length, which means that these are the ones that should determine the support of my vector x. And once I determine the support, I'm done because this was the hard part. Okay? Of course, we don't know what the optimal value of C is, but here is an observation. So we don't know C, but let's say that, let's focus on this gray area around the optimal C. So let's say that we have some C that was slightly suboptimal. Now, if I move my vector C from the optimal position, I expect that the lengths of the projections will change. But I'm not, at this point, I'm not really interested in the exact lengths of the projections. I'm just interested in the relative ordering of these lengths. Okay? So you will see here, these curves present how the length of the projection changes as I move this vector C. So this is just the spherical coordinate of this vector C. So as I move my vector, the lengths change, but there is an area around the optimal one where the sorting of these lengths remains the same. And I can do that for the entire circle, conceptually, right? So what I do is I get these curves of how the length of the projection changes as I move C around the unit circle. Now the key is the following. What I'm interested in is which curves are at the top S positions, because this will determine my support. So if you keep track of these curves, you will see that there are basically regions in which the top S curves remain the same. So let's say that I'm tracking the two highest curves. In this area, it's the green and the blue. Then there is an area where it's the green and the purple, and so on. Okay? And the question is, when does the sorting of these curves changes? So a necessary condition for the sorting to change is actually that the curves intersect, at least 2 curves intersect. So I have n curves. Each one corresponds to a dimension. And there are at most n choose 2 points at which they intersect. In fact, I should say that my curves intersect at, every pair of curves intersects at most 2 points, or exactly 2 points. So I have order n square points of intersection, which means that my candidate support, the top S curves change at most order n square points. Okay. So someone would naively say, I have a target sparsity S, which I unfortunately chose to be 2 here. But in S could be arbitrary. Okay. So naively, we would have order n choose S possible supports. But exploiting the fact that our input matrix is rank 2, we can actually reduce that to order n square candidate supports. Okay. And just like if that was not very clear, let me just say the following. Like this was the key observation in this tool. Let's say that someone gives you n arbitrary curves, okay, and then they ask you to keep track of the highest in magnitude S curves, okay. Then, in general, if the curves are arbitrary, then we could make it so that all groups of S curves appear at the top at some point or another, and then we would have to consider all n choose S supports. But the main observation here is that in my case, these curves are not arbitrary; they are sinusoids. And if I am in 2 dimensions in the rank 2 case, then I can upper bound the number of intersections by order n square intersections. Okay, that's the main idea. And this idea generalizes to higher rank. So I can do the same trick without actually plotting it in R dimensions. I will no longer have like 2-dimensional curves. I will have, imagine some hypersurfaces in 3 dimensions and whatever you can imagine in higher dimensions. But the same trick still applies, and I can develop a bound that instead of n square will be n to the r. Okay. So an overview of how the algorithm works. The input is a PSD matrix n by n of rank r, as well as the target sparsity S. The first step was to compute a factorization VV transpose. The second step is to use this gadget that I just described to get a collection of candidate supports. Once I form this collection in time n to the r, I can actually exhaustively compare every support and find which one corresponds to the best solution. And I will just output the best candidate. So what have we accomplished? What we have done is we have found a way to exactly solve the sparse PCA problem on a rank R input in time of order n to the r, n to the r plus 1 here.
Can you go back 1 step? Can you go back 1 step? At the end, you apply it on the A matrix, not AR. Yeah.
Mistake. Okay. Yeah, this is a mistake. It should say AR.
I see. But you can do that, yeah. You can. I mean, if you have a matrix which is not even rank R, so you just extract the approximation of rank R and then compute the supports, and then at the end, but do the sparsity on the A.
That's very correct.
Yeah.
But let me just, using this opportunity, make a couple of remarks. To get the desired complexity, I actually have to do it. Even if we say that the original input is a full rank input, and then I did the low rank approximation, now I'm solving the low rank problem. If I could, indeed, when I find the support, I could test it on the original matrix. I would get better results. But to achieve the desired complexity, I mean, it would add a little bit of complexity.
Basically, it doesn't guarantee that the optimal is not guaranteed.
Sure. But the guarantees I gave anyways just rely on us computing the component on the low rank matrix. And we also have a computational gain doing it on the low rank matrix instead of the large one. Okay? But thanks. Okay. So one almost final remark is the following. So we said the original input was not low rank. We have an algorithm to solve the low rank problem exactly. Someone might say, okay, why do that, since we are already working towards an approximation? So here is an idea for an approximate and faster algorithm. So I drew this gadget earlier, and I said we use this to find the optimal support. And the whole idea was that I could essentially find all possible, or construct actually a collection of supports and then guarantee you that the optimal support will be among one of them. Okay? And the way we did that is we have a way to compute the intersection of these curves and then find all the points at which the candidate support changes. But another thing we could do is we could exploit the fact that this vector C lies in a low-dimensional space. So we could just go ahead and exhaustively sample. Okay? So given some parameter epsilon, we can actually create an epsilon net in the two-dimensional unit circle. And we can do that in a higher dimensional, also in the higher dimensional case for general rank R. Okay? And then once we, for every sample C, we fix C, we solve the rank 1 problem, and we get a candidate. Okay? And then we just, again, output the best candidate. So what this does is it gives us a way to get an approximate solution. So we have an approximate solution for the rank R sparse PCA problem, and which gives us a solution that lies in terms of the objective function always. It lies within a 1 minus epsilon factor from the optimal. And what we have accomplished is to move this exponential dependence on R from the dimension n to a constant factor 4 over epsilon. Okay? Okay, so experiments in this line of work, especially since we're interested in the objective, are just usually tables of numbers, so this would not be very interesting. So let me just use this as an example. Let's say that you have, what we did, we got a document corpus. This was from a collection of articles from the New York Times. And we ran this sparse PCA approach. Okay? What we could do is actually find a component, then remove the words that we used, and repeat. In fact, this particular example is from an extension of this work where we try to find multiple components at the same time. But what we're trying to do in any case is find sparse components that have correspond to disjoint sets of words. Okay, and you see that it's interesting, it was interesting to me at least, that the components that we came up from this algorithm tend to have some meaning. So you will see, like, as I mentioned earlier, one topic corresponding to recipes, perhaps some with reference to economy or foreign policy or, I don't know, war. Okay. And then on another example dataset, this was a small dataset on a bunch of face images. Yes?
In your previous table, how does this compare to sparse LDA?
I did not do this comparison. So as I said, I use this example mostly as a motivation. I'm not claiming that, especially in this qualitatively, like, I could not compare with another algorithm. This was not my intention. But it was mostly to get an idea of, intuitively, a sparse component can actually have a meaning in a physical system.
Yes, it's a follow-up to that. So one of the things you can do with topic models to get these interpretable results would be to take your vector and take the words with the highest weight in your topic, which would correspond to your rank 1 approximation. Do you have like an intuitive sense of what the rank 2, rank 3 gives versus just taking the highest ranking?
Okay. So very well. So first of all, let's repeat that one solution to the sparse PCA problem, one heuristic would be to do the rank 1 approximation, or not the rank 1 approximation, I'm sorry, to do vanilla PCA, find the principal component, and just do a hard thresholding, keep the largest entries. Now the problem is that, at least in terms of the objective function, this is quite suboptimal. This is why we are interested in the sparse PCA in the first place. Like, how can we find an algorithm to find a component that is sparse, but also performs better than this heuristic? Now, in the context of the modeling problem that you mentioned, I don't know how well that performs, but I can tell you that increasing the rank and finding a solution for higher rank does improve significantly, like you may double. I mean, it depends always on your data set, but it improves at least in terms of the objective function. The objective function may not be what you are interested in the end of the day, but that's what I looked at, and in terms of this objective function, it does improve. Okay. Okay. So this example, I only have it here to do the following remark. So we got this data set, it was with face images, and we ran sparse, and in fact we ran sparse and non-negative PCA on this one to find one component. I'm playing here with the support of the cardinality of the support, so I'm looking for a vector with only 20 non-zero entries, up to 200 non-zero entries. I'm gradually increasing the support, and I'm plotting this objective function, the explained variance. Okay. I mean, clearly, as we add more and more elements in the support, we have more flexibility, we get a better objective function. That's not the important thing. The important thing is that using our algorithm, we can actually, even for rank 2 or 3, where we're actually able to run the algorithm, we can get some approximation guarantees and say that the objective function, the objective value we achieve is, 50% of the optimal. And this example is not the best one in terms of guarantees. There are other datasets we have got better guarantees, but you never know. Like, it depends on the spectral decay of your input. Okay. So, last slide. What I have done is I presented a novel algorithm for Sparse PCA. This algorithm comes with some form of provable approximation guarantees. These guarantees are spectral, and they also depend on your input data, so the data-dependent guarantees. I showed you that under simple assumptions, you can get some theoretically interesting guarantees, like, for example, a PTAS for any kind of spectral guarantee, like a power law decay in the eigenvalues of the original input. And we showed an algorithm to solve the problem exactly on a low rank input. And then I argued that basically we can go about and solve the low rank problem approximately. And this allows me to play with the choice of the parameter R. So I can choose a large R and do a sparser sampling. I'm given a time window, and I can just output the best output in this time window. And it has also this sampling algorithm. Actually, the entire framework can also be very trivially parallelized. Okay, so it has also this computational benefit. And in practice, we have seen in many datasets that we always perform at least as well as other approaches for the same problems, at least in terms of the objective function, that it's something that we can quantitatively compare with other methods. And I think that would be all for now.